let's solve exercise 2.2. A monkey types on a 26-letter keyboard that has lowercase letters only. Each letter is chosen independently and uniformly at random from the alphabet. If the monkey types 1 million letters, what is the expected number of times the sequence proof appears? So I guess the intuitive approach to this is say, all right, so if we say we have 1 million letters, so this is the first letter, this is the second letter, and this is the 1 millionth letter. There are a total of 26 to the power of 1 million combinations of letters available. That is obviously true because, in each place there can be 26 types of letters from A to Z, lowercase only. 26 on each. So we multiply 26 1 million times, and we get 26 to the power of 1 million. Now, let's say how many combination of letters will have only one sequence proof, right? So we can see that one such case will be something like this. Another case will be something like this. So there, the sequence proof appears for the front five letters, and then in the rest of the letters it doesn't appear. And the second case is when the sequence proof appears in the second, third, fourth, fifth, sixth letters, and then for the rest of the letters doesn't appear. And this can go on and on until the combination of letters in which the sequence proof appears in the last 5 letters. So the total number of cases when the combination of letters have only one sequence proof is 999,996. Okay? Because this is gonna be 1 million. This is gonna be 999,999. It's gonna be 999,998, 999,997, 999,996. There's 999,996 cases. So the probability that there will be only one sequence proof is 999,996 over 26 to the power of 1 million. Right? So when we want to get the expectation for the number of times the sequence proof appears. We do 1, okay, times 999,996 over 26 to the power of 1 million. Okay, plus, next we have to consider the case when there will be 2 times when the sequence proof appears. This is gonna be, again, 26 to the power of 1 million. And there will be some number over here all the way to this 200,000 times 6, 1 over 26 to the power of 1 million. The reason why I am using 200,000 as the maximum number of times the sequence proof appears is because when we pack the sequence of letters full of pure OOF proof from the start to the last, all the way to the last letters, it can contain 200,000 letters. That's why. Okay. And there's only one case, right? When there is 200,000 times of the sequence proof, because proof is because the only case is when the combination is packed full of this, right, from the start to end. So when we are trying to calculate this expectation in this way, we have to calculate the probability that each number is gonna have, and this is quite impossible because it's very complicated, and if you try, you're gonna hit a brick wall. So what we have to do is we have to go around this problem. Okay, so we don't use this, right? So the way we're gonna go around this problem is we're gonna say that we're gonna declare a Bernoulli random variable. Random variable xi. And xi is gonna be gonna be 1 or 0 because it's a Bernoulli random variable. So what this random variable does is, when, let's say, this is the first letter, and if the sequence proof starts from the first letter, then xi is gonna be true, so it's gonna be 1. If pure OOF doesn't start from the first letter, x1 is gonna be 0. that is the Bernoulli random variable. And the way we are going to do this is we're going to get the expectation of EXI x1 plus x2 all the way to x999 996. What this does is essentially it does the same thing as this one. Because it's saying for each combination of letters, if x1 plus x2 plus x99996 is equal to 1, it means that the sequence proof appeared one time. And the probability that it appears one time is this. Okay? But the problem is we still cannot, calculate this if we are just going to use the same way that I have described before. So what we use is the linearity of expectations. The linearity of expectations is actually in the textbook. For any finite collection of discrete random variables x1, x2, xn with finite expectations, this is equal to this. So we use that, and we have EX1 plus all the way to EX999 996. And the thing is, we can easily know that the probability for this, for xi, is always, the probability for xi is always 26 to the power of 5 with 1 over it. So essentially, this is equal to 999,996 times 26 to the power of 5 with 1 over. So the answer is 999,996 over this. That's the answer to this question. So the key to this question is that we use the linearity of expectations, which is rather unintuitive. Because if we use the intuitive approach, it's impossible to solve. It's nearly impossible to solve this. So we use the rather unintuitive approach, which is linearity of expectations, to solve this problem. Now I recommend you to think more about this, because and to try solving this by yourself after some time, because this is a rather tricky question. That's it.